frontiers of science sounds, of course, a little bit counterintuitive for the topic which we have at hand here, meaning Moiré graphene. But this is a continuing series of conferences which is organized by ICFO throughout the years, which are usually centered about some aspects of light. But this year we will talk mostly about magic angle graphene. But as you will see, we also have a lot of topics which still have to do something with light. So just a quick introduction for many of you who maybe haven't been to ICFO. So first of all, it's a pity because it's the summer in Barcelona right now, and we would have loved to have you all here. Unfortunately, we have to do it online, but I think it's still a very excellent program which we have, and hopefully this will be a nice success. And also the list of participants is quite excellent. And also the amount of attendees is breaking a few records here. So we have right now more than 300 people being live in this broadcast. And more than that, we have more than 800 registered participants. Okay, so just a few words about ICFO itself. So ICFO is a multidisciplinary institute in Barcelona, in Spain. And it is an institute which deals with many aspects of light. But it's really multidisciplinary. So we have really people here which work on transport properties, with optoelectronic properties. We have people who work on cold gases and try to make Moiré graphene. So we're really a multidisciplinary institute. I also want to thank the funding agencies which have supported this conference. So first and foremost, CELEX, which is a private organization which supports with their donations. We also are very thankful to the government of Catalonia with the Risk Cuts program. And as Pablo Carrillo Herrero will introduce in a bit, we have also strong ties with MIT, and they are also very helpful in organizing this event. So with this, I want to first pass on to Frank Coppens, who will discuss a little bit about the format of this event. Frank?
Okay, thank you, Dima. So to me, this is a very special event, not just scientifically because the program is really amazing, but also because it's format. So we were forced to do it online due to COVID, but I think this is now also a new paradigm in terms of how we communicate as scientists to the world. Because in this format, we are really able to reach out to a much larger amount of people than we usually are at conferences. And so I'm extremely glad to see that we have more than 850 registrations, which is 5 times more than we would otherwise be able to fit into the building. And accessible now to many people that would otherwise also not be able to come or be able to afford to come. So this is a really great event. And I feel that this is really a change now in our scientific community to not only serve the society to disseminate science to everybody in the world, but also to serve the planet by flying less. So let's keep this momentum in serving our society and our planet and disseminate at the same time science over the world in a better way. So not only Moiré materials are a game changer here, the way of communicating science is also shifting in paradigm. And I want to welcome all of the 850 people. I see now there are already 333 online and the number is still growing every second. So according to my calculation, we are at 800 in a few minutes. So thank you very much, everybody, for joining. And now we give the word to Pablo Herrero.
Thank you, Frank and the man. Hello, everyone. It's a pleasure to welcome you virtually. I don't know if you can see my background, but this is what the Castelldefels beach looks like. Dima, Rob, and Frank get to enjoy it every day. I was very much wishing I would be there to enjoy it, but at least I can show you virtually. And as Frank and Dima said, this is this is something that should have happened in person. It's not happening in person, but at least the silver lining is that we get to reach to many, many more of you. That we hope you will enjoy talks by our great speakers. And I think that Frank said, probably the future is going to be some kind of hybrid, where we have these type of online events, but of course we also hopefully will get to enjoy the in-person interactions, which are also very important for, from a human point of view, and also for science, So with this, just welcoming words, I want to hand it over back to the chair, I think it's Dima, so that we can introduce the.
Okay, I have also. I also forgot, I need to mention the Optical Society of America and SPIE, who also supported this conference. So we're very grateful for the support. And then, of course, I want to introduce our introductory speaker. So we've designed it so that such that Pablo Jalil Herrero would give the last talk of the conference to summarize all the developing events, and Allan MacDonald will begin the conference. Of course, as most of you know, Allan MacDonald is now at the University of Texas in Austin. Allan MacDonald is most famous for pioneering work in the quantum Hall effect and the spin Hall effects, for which he received the Buckley Prize. And of course, Allan MacDonald is famous for his work on 2D materials. Now, I'm not sure if it's most famous. Maybe by now it's the most famous work by Allan MacDonald is the prediction of magic angle graphene and the coining of the word magic angle. And with this, handing over to you, Allan. Thank you very much for attending.
Okay, thanks, Dima. It's amazing how this subject has developed since I started working on it many years ago, originally with Rafi Bistritzer, who's now at Applied Materials in Israel, and Fengcheng Wu, who's now at the University of Maryland. And I want to acknowledge at the beginning the great fun I'm having working on related problems with colleagues and students and postdocs at the University of Texas and some around the world, and also experimental friends who've let me puzzle about some of their experimental results, which is always great fun. First problem.
I think
it's not letting, go ahead. It doesn't seem to let me advance. It's not a problem I've had before.
Can you scroll the mouse? Sometimes that works.
It was working before.
It was working before, yeah.
Okay, sorry about this. Let me stop sharing. Maybe
right,
that's
okay.
what happened. I'll start again.
Okay.
No.
Could you, it says somebody comments that you can try to click the screen first. Yeah.
Thank you.
Okay.
Thank you, whoever said that. Okay. So I'm sure many of us would rather be having this meeting in person in Barcelona, but that's not to be. But I'd also like to take the opportunity to thank MIT and ICFO for putting this meeting together, and also for their pivotal role in this subject, starting from the discovery experiment at MIT. So since I'm the first speaker, I'm going to try to provide a little bit of an overview for those of you among the audience who haven't really been following this subject. So Moiré materials are basically artificial 2D crystals formed by making periodic patterns by overlaying 2D crystals. What you see in this picture is an overlaid blue and red honeycomb lattices. And you can clearly see the longer length scale pattern where the local stacking through space is slowly changing from AA stacking to more close pack stacking, and forming a triangular lattice pattern. And so that's the periodicity that is acting to create artificial crystals and artificial strongly correlated crystals. And as I said a moment ago, it's really quite magic and amazing how this subject has developed through experimental discovery. These Moiré materials are, as made in the lab, just from their observed properties, it's clear that they're very nearly perfectly periodic, more perfectly periodic perhaps than we can make with any lithographic technique. They also have the property that you can tune how strong the correlations are, how the ratio of bandwidths to interaction scales just by changing twist angles in different overlaid 2D materials. And of course, that occurs in a very special way in the case of graphene bilayers. One of the things that works out very nicely in these materials is that the Moiré patterns usually end up having length scales that are around 10 to the minus 12 square centimeters. And that is really just perfect for not being too small, that the system would be too sensitive to disorder, but being large enough that you can change the number of electrons per period over the relevant range just by gating. So those are some of the interesting things about these materials, or this class of materials. And already, and I hope this is early days in this subject, we've seen a number of unexpected and interesting observations. One of the things I will talk a little bit about today are the churn insulator states that have been discovered in twisted bilayer graphene and the associated magnetic properties. There are also observations in the case of transition metal dichalcogenide systems, which, as I'll explain, are described by Hubbard models of Wigner crystal states that have never been seen in real crystals, because probably because they're end up being obscured by doping disorder in the real crystal case. And perhaps most interesting of all is the fact that these, in the case of magic angle twisted bilayer graphene at least, these are, the electronic system is superconducting, and superconducting at densities incredibly close to densities at which the system is insulating. So let me start by going through what is the simplest example of simplest type of Moiré crystal in principle, and that's made from transition metal dichalcogenide 2D crystals, which, as most of you know, have a valence band maximum at the Brouin zone corners, K prime points of the Brouin zone, where there is spin splitting. And so we're interested in knowing how the states of a single layer are influenced by a Moiré pattern. And first thing that we can invoke is the fact that everything is smooth in space in these Moiré patterns. So that means that momentum is conserved, at least closely enough that we can concentrate on states at one Brouin zone corner or the other, these two distinct momentum points. And at those momentum points, it happens in these transition metal dichalcogenides that there's a large spin orbit splitting. So in the crystal, before we establish the Moiré pattern, at a given momentum region, which I'll call a valley, there's only one state. not even a spin degree of freedom. And so the general way of thinking and building or a way at least of thinking about the Moiré crystals and about how to understand their properties on the basis of microscopic calculations is by this kind of argument I will now give, which at least briefly, and which only applies in the case of semiconductors and semimetals. So that's one of the ideas I want to get across, that semiconductors and semimetals are especially simple in their Moiré crystal properties. And the reason is because although the entire band structure of this 2D system is changing as I change the stacking arrangement. For example, I can change the stacking by rigidly moving the blue layer relative to the red layer. Of course, that's happening in a smooth way as a function of position in the Moiré pattern. And I can, if it's smooth enough and we're only interested in states in a small region of momentum space, I can just keep track of how the band Hamiltonian is varying at a central momentum. And in the case of a single band, that means there's just an effective potential that depends on position. And so if you apply that recipe, for example, to the case TMD system, tungsten disolenoid on molybdenum disolenoid or disulfide, they're all kind of similar, then you find that the top of the valence band moves around in space as you change the stacking arrangement. And in the Moiré potential, in the Moiré pattern, that leads to a effective potential for the spinless electrons in a particular valley at the top of the valence band. And the size of this modulation potential is a nice energy scale, not too small, but still small enough that we can control it with the same without changing the underlying chemistry. And yeah, so in this case, that modulation potential varies with a fixed strength over a period that you can vary, the Moiré period that you can vary by simply varying the twist angle. For a small twist angle, it takes, you have to go a large distance before the stacking repeats. And so you get potential of fixed strength that varies periodically over a control length scale. And by making that length scale small, you can make very flat bands, nearly localized states out of the states that are concentrated near the extremum of the potential. And so basically these systems I've been talking about so far are described by a particle in a periodic potential. It's easy to get in the narrow band regime. Interactions, at least part of the dominant interaction is on site, like in a Hubbard model, although longer distance interactions are certainly, experiments show, also have an importance. Yeah, and the wave functions are quite localized.
Dear Allan,
go ahead.
We have a question for Maciek Levenstein.
Okay.
Maciek, do you have a question?
I don't know. Am I speaking through my stomach?
I can hear you. I can hear you.
Yeah, but I didn't have any questions. Sorry.
Oh,
Maybe
okay. So you raised your hand. Sorry about that then. Okay, you raised your hand. So this is
probably I raised my hand
unconsciously.
I'm sorry.
Yeah. All right.
So
sorry about that.
that kind
But
of.
at least it works.
Yeah. Okay. Now we tested it.
Yeah. Okay. So.
Oh, sorry. Okay. We immediately
Go
have
ahead,
another question.
Dima.
Okay.
What is it?
Sorry. No, we don't have any more questions. Sorry about
Okay.
that. Yeah.
Okay, so indeed, several different researchers have realized that type of strongly correlated system. And one of the interesting things about them that's ICFO related is they can, these TMD systems are naturally probed optically. And I've shown on the right here, just as an example, from this paper from the Cornell group, a measurement, which is basically a measurement of spin polarization in the presence of a magnetic field, basically measuring the magnetic susceptibility of an artificial insulator that's probably magnetic at low enough temperature, although these measurements are done above the temperature where there's a Curie Weiss type magnetic susceptibility. Okay. So that's, those are TMDs which are, in which the top of the valence band is near the gamma point. I should have mentioned that the spin is in fact locked to momentum in this system, so the Valley degree of freedom can be viewed as a spin degree of freedom. So it's, you know, the system acts like a particle in a periodic potential with a spin degree of freedom and a very weak spin orbit coupling. Here's another example of a different type of moire that's not yet been realized experimentally, and I'll mention a couple of these. This is for a HOMO bilayer of a TMD like tungsten diselenide. Many TMDs, when you include the coupling between the layer, the coupling of states at the gamma point in the Brouin zone. Question? Okay, so the states at the gamma point in the two layers form basically, you know, bonding and anti-bonding bands, and they actually, states at the gamma point, unlike states at the Brouin zone corner points, actually couple very strongly. And the end result is you get a single relevant band spread across a bilayer. This figure here is from work that I was doing with a visiting student from CISA, Mattia Angeli. And what it shows is that the modulation potential in the case of these gamma band based HOMO bilayer systems is stronger than in the K-based systems. And also the emergent symmetry in the continuum model is that of a honeycomb lattice, not a triangular lattice like in the other case. So there actually end up being 2 bands per unit cell for every minimum in this modulation potential, which opens up some new possibilities for study. This is an example of comparison with full DFT of a simple model of the type that I've been describing to you, and full DFT calculations. On the right-hand side, you see Moiré band properties at smaller twist angles where it would be nearly impossible to do the calculation microscopically. And these bands are calculated with the model of a particle simply a particle with a spin degree of freedom in a potential that has a symmetry of a honeycomb lattice. And so you get artificial graphene type systems, you get systems which you get many, may have orbital order, many things are possible in this type of system. And another type of Moiré that has not yet been realized experimentally is K-valley homo-bilayers. In this case, the splitting between the bonding and anti-bonding states in the two layers is much, much smaller, as is well known. And for that reason, this is actually a two-band model, which at least if things work out just right, can give you a described by a two-component Hamiltonian, with a layer pseudospin degree of freedom, and an effective magnetic field that has the skyrmion structure in space, which leads to topological properties of the bands. So those are some of the let me just skip this one. This is just a model band structure calculation we calculated a couple of years ago for a K-valley based homo-bilayer system showing topological bands I mentioned. So I gave two examples of Moiré Hamiltonians that should be realizable in TMD systems in time. And it's also possible to realize artificial periodic Hamiltonians for excitons, for bosonic collective excitations of the system. So there's, I think there are a lot of possibilities in TMD systems. But I'm going to spend most of the rest of my time talking about magic angle bilayer graphene. So following along the same way of thinking about the Moiré structures, the low energy states of a single layer of graphene, as you know, there are two bands at low energies, which are associated with the fact that graphene is actually a honeycomb lattice, and there are two carbon atoms with pi orbitals per unit cell. And so if I make a bilayer by twisting one graphene layer relative to the other, that means that I have four component spinor wave functions. Every wave function in the Moiré has components on each sublattice of each layer. And so the periodic Moiré Hamiltonian in this case is a 4x4 Hamiltonian. And if you follow the same philosophy I was explaining before, this 4x4 Hamiltonian is in the case of a Moiré, a periodic function of position. And the most important way the two layers influence each other is because electrons can tunnel between the layers. It's well known, for example, for AB or BA alignment, the tunneling between the layers changes the electronic structure qualitatively. What I'm showing here is a picture from my paper with Rafi Bistritzer some years ago of interlayer tunneling. This is actually looking at tunneling from a B sublattice of one layer to the A sublattice of another layer as a function of position. This kind of model in which this periodic, every tunneling amplitude is sublattice dependent. So there are four of these amplitudes and all complex numbers and all functions of position. and with the expected properties at the high symmetry points. For example, for AA stacking, that hopping between the A sublattice and the B sublattice goes to 0. So this kind of model has been tested and improved in more recent work, for example, by Xiang Fan et al. And others, but it's qualitatively correct. And it leads us to this surprising result that we obtained using this type of continuum model approach. Same kind of result was actually obtained by Morel et al. Using tight binding models, and which led to the expectation that there should be strong correlation physics in this system if people could actually make samples with controlled twist angles, which was not at all obvious when we were doing this theoretical work. And so the model I just described with periodic, local, sublattice dependent tunneling between two graphene layers, each of which has a Dirac cone, leads to the following type of electronic structure. If you go to larger twist angles, here even for 2-degree twist angle, you can see partly the remnant of the original Dirac cones at the 2 Brouin zone corners. There are Dirac cone for each layer, but they're at slightly different momenta because of the twist. And you can see, I want to draw your attention here to the fact that at 2 degrees, the states at gamma are, the gamma point in the Moiré Brouin zone are furthest from being degenerate. But between 2 degrees and 1 degrees, these states collapse and you get this extremely flat band, extremely flat compared to the energy, the overall energy scale of the system. And another thing I want to draw your attention to is that in this calculation, you can see that what we often refer to as the remote bands. So at zero energy, near zero energy here, there are 2 very flat bands. Then there are states that are far away in energy, except at the gamma point in the Brouin zone. So this is something I'll come back to in a moment.
Allan?
Yeah.
We have one, we can try one more time to have a question.
Okay.
Because this is, I think it's good if we have questions along the way as well.
Yeah.
So with Valerio Vitale raised his hand.
Yeah.
Okay.
Can you hear me?
Yeah, we can hear you.
Yeah, so now the question was more about TMDs and what's the role of relaxation in the bed structure. You show how these change, especially the valence bands and the top valence bands.
Yeah, so the relaxation changes the profile of the potential, but it's still periodic. I didn't emphasize, but we usually, describe these periodic potentials in terms of just 1 or 2 phenomenological parameters. And based on an argument that we expect the potential to be smooth, and therefore we can expand it in terms of the Fourier components of the first shell in reciprocal space. And then if you use whatever symmetries are present, that will reduce the number of parameters to 1 or 2. When relaxation is important, then it will certainly change the strength of that periodic modulation. But if you have, really start to develop basically grain boundaries in the stacking arrangement, as you will at very small twist angles, then you probably need higher harmonics in this type of phenomenological description of the electronic properties. Okay, so that's a good question.
Okay, and one more quick question, last question by Maximilian Kogel.
Go ahead.
Maximilian? We cannot hear you. The microphone seems to be on, but we cannot hear you.
Can you hear me right now?
Yeah.
Oh, okay, sorry. So my question is also about TMDs, and I wanted to ask, what does define the magnitude of the Moiré potential? Is it the Moiré wavelength? Is it the TMDs that are defining the heterostructure?
Yeah, within the local picture that I described, the magnitude of the potential is completely independent of the twist angle. It's when you change the twist angle, you just change the length scale over which the stacking arrangement changes. So the same strength periodic potential occurs with a period that depends on the twist angle, and that kind of picture is certainly approximately correct, and has predictions, has consequences for example, the fact that in the TMDs, when you go to small twist angles, you always get narrow bands that are basically separated by some harmonic oscillator length scale associated with the minimum of the potential. And so in the TMD case, the bands just get narrower and narrower the smaller the twist angle, and the physics that's accessible, that controls the physical properties, is very similar to the textbook idea of varying the properties or forming bands from an atom by broadening the bands, or going between the crystal and atomic limits by narrowing bands. So here we can really do that just by varying the twist angle. But in the case of magic angle twisted bilayer graphene, the nature of these flat bands is quite different. They just appear at discrete twist angles. They don't get narrower and narrower the narrower the twist angles, because they arise from some kind of periodic phenomena that we understand fairly well, but still only partially, and we may hear more about that from Ashwin Vishwanath later in the symposium. So let me go on. Let me mention before, on the last part of my talk, and our chair will tell me when I have to quit, last part of my talk, I'm going to talk about two aspects of the physics of magic angle twisted bilayer graphene at a twist angle where the bands get very, very flat. And I'm first going to talk about Chern insulators and orbital magnetism, which is, I think, is quite a charming, amazing magic story, if you like, but is at least partially understood. And then at the end, I'll talk a bit more or less around the topic of superconductivity, which is less well understood right now. But before I start on that, I want to highlight three not especially profound, but nevertheless important and pesky problems if we really want to have predictive theoretical models of magic angle twisted bilayer graphene. One is an issue that people already mentioned, which I slid over at the beginning, which is the issue of strain. The atoms in the two layers relax relative to the rigidly twisted layers. And another important single particle property is particle hole asymmetry. So let me start with the single particle properties. And the main idea I want to say in magic angle twisted bilayer graphene is that when you're very close to the magic angle, the broad graphene bands somehow get folded down into extremely flat bands. But if we're interested in the physics of those extremely flat bands, one possibility is that they're so flat that the dispersion of those flat bands simply doesn't matter for any observable property. We know, I think, from many experiments that that's not really true. But if that's not true, then whatever dispersion does remain in these flat bands is very sensitive to details. And one important detail is what's going on at the gamma point in the Brouin zone. I should have pointed out, and you may have noticed in the magic angle calculation by Rafi Bistritzer some years ago, the remote bands and the flat bands practically touch just at the gamma point, although they're well separated at other points. It turns out that that when you add strain effects, there is a better, more separation between the flat bands and the remote bands, and those strain effects are certainly there. In the cartoon I'm showing here, the strain effects can be partially mimicked by because they basically expand the regions with local AB stacking. They can be mimicked by reducing the hopping, strength of hopping on the same sublattice. And one thing that can happen at the gamma point in twisted bilayers is that states always occur in positive negative energy pairs, but those positive energy pair states can each be doubly degenerate at the gamma point. And you can see this is a color plot, color scale plots, white for small, blue for large, what we want, just to simplify the problem, energy separation between the flat bands and the remote bands. And there's this swath here where the separation is very small, and it's just near the magic angle, and it's very sensitive to TAA over TAB twist angle. And this separation between the flat and remote bands going to zero is a property of doubly degenerate bands passing through each other at the gamma point. And so that property is nearby in the parameter space of models that we might use to describe this, although probably most of the experimental results are here above the magic angle, and the strain effect actually serves a very helpful role in separating the flat bands from the remote bands. We probably don't know exactly how well separated they are, however. And the second point I wanted to mention, which was emphasized to me by Stephen Carr, is that in more accurate models of the flat bands, the energy separation between the flat bands and remote bands is larger on the conduction band side than on the valence band side. And that particle hole asymmetry is really due to non-locality of the interlayer tunneling that I was describing earlier in a local approximation. So just to summarize, there are little details that we don't know very well that affect the dispersion of the flat bands. And of these three mundane but pesky problems, the third one is probably the most troublesome. And that is illustrated here. What this is illustrating is that the flat bands are, even if the remote bands are far enough away in energy that their quantum fluctuations are not important, even when they're frozen, they have mean field interactions with the flat bands, which change the dispersion of the flat bands. This would not happen in the TMD case, for example, where the remote bands are localized orbitals, and they don't affect the, may shift the energies. Interactions with the flat bands, with the core levels, if you like, may shift the energies of the orbitals you're interested in, but it doesn't change their dispersion. That's not true at all in magic angle bilayer graphene, because the actual orbital character of the wave functions changes throughout the Brouin zone. In particular, it's very different at this pesky gamma point than it is through most of the Brouin zone. In this plot, for example, you see this is a calculation for some model interaction strength of the mean field shifts in the flat bands due to interactions with frozen remote bands, and what we refer to as the remote band self-energy. And you can see this characteristic property also emphasized in work by Paco Ganea, may be cited later, that that the energy levels in the flat bands are shifted up at the gamma point, here by so much that the valence band or conduction band is shifted all the way up to the remote bands. And in the valence band, instead of having a band minimum at gamma, as you would in the single particle picture, you actually have a band maximum. So so we don't know, for example, we don't know what the Fermi surfaces look like in this system. It would be wonderful to have photo emission experiments with enough resolution that they could actually tell us the shape of the Fermi surface in these systems and where they're located in the Moiré flat band. Okay, so in my remaining time, I will talk about two aspects of the physics of magic angle twisted bilayer graphene that have been quite well developed, at least on the experimental side, and that is that insulating states are common. And if you look at the flat band properties, then even at neutrality, it's perhaps not immediately obvious why you should get an insulating state, because the flat bands, of course, occur in pairs, conduction valence pairs, but they have a symmetry which causes them to touch at the Dirac point. And the Dirac points, in other words, of the isolated layers in the bilayer system is not lifted, that degeneracy is not lifted by coupling between the layers. And first thing you need to do to get insulating states, which of course are very common experimentally and seen most of the time at insulating filling at integer filling factors, integer numbers of electrons per Moiré period. When I use filling factor, I'll use the language where there are 8 states per electron in the Moiré band, 4 for the conduction band, 4 for the valence band, 4 because of spin and valley degeneracy of all the states. And so the easiest way you can understand why the Dirac points should be expected to be gapped in these systems, especially at integer filling factors, is by recognizing that the evolution of the bands, as you start from large twist angles where the layers are essentially isolated, has the Dirac velocity gradually decreasing. And already in graphene, it's known that when you have Coulomb interactions and you have a 2D Dirac model, you expect a density wave state to form, which gaps graphene. Before people studied graphene experimentally, theorists thought that this might happen in isolated graphene sheets. Turns out it doesn't because the velocity's too big, but the velocity, as the velocity gets small in this graph, approaching the magic angle, this is a line here in momentum space where mean field calculations estimate that in bilayer graphene, magic or twisted bilayer graphene, you break this time reversal like symmetry or inversion like symmetry, maybe I should say, and open up a gap between the conduction and valence bands. And so that does appear to be going on in graphene. And just like in single layer graphene or bilayer graphene, when you open up a gap, you get a half quantized Hall conductivity per flavor and per layer in this system. And so the bands become topological, or actually develop Berry curvatures, and which has an important consequence, as I'll come back to in a moment. So we have gaps. The gaps are, you can think about the criteria for forming gapped insulating states in terms of a Stoner criterion. As you go above the magic angle, the width of the flat band grows very quickly. And for a large enough deviation away from the magic angle, you'll get, it will exceed the typical interaction strength. And as I showed you a moment ago, you may not get the symmetry breaking, but you also may not get flavor symmetry breaking, creating spin gaps not only between different spins like in a regular magnetic system, but also between different valleys. And so this flavor symmetry breaking at integer filling factors allows the gap to appear not only at nu equals 0, but at all non-zero filling factors. And I want to concentrate for a while on filling factor 3. Filling factor 3 is one missing, one band, if you like, one band per flavor empty out of a full flat band system. And as many of you know, at filling factor 3, people have observed the quantum anomalous Hall effect in graphene. And that quantum anomalous Hall effect can be understood as a consequence of the topology of the valley projected bands that I was referring to just a moment ago, combined with polarization of all of the missing states in a single valley. So just as Coulomb interactions, Coulomb exchange interactions favor spin polarization, they also favor valley polarization. And this is just an amusing example. The valley polarization that occurs in twisted bilayer graphene, or at least is thought to at nu equal 3, and is exactly the same thing that Werner Heisenberg and Fritz London discussed in the 1940s in a series of incorrect papers trying to find a theory of superconductivity. They argued basically because of exchange interactions that electrons in a metal would condense in momentum space and that this might be responsible for superconductivity. So it's not responsible for superconductivity, but it is responsible for, it is broken time reversal symmetry, and it is responsible for orbital magnetism. The states at filling factor, insulating states at filling factor 3 in magic angle twisted bilayer graphene. Experimentally, the statement I just made is only true when you put it on an HBN substrate. I can come back to that if somebody asks. They are Chern insulators. They have broken time reversal symmetry. They have unequal occupation of bands in different valleys that have non-zero Chern numbers because of the Dirac cones combined with the broken sublattice symmetry. And so it's interesting to compare this kind of Chern insulator, which I think is the second class of system in which Chern insulators have been measured in experiment. Both systems are different from the toy model system that Duncan Haldane dreamed up when he wanted to make the point that quantum Hall effect could occur without a magnetic field. But in the graphene case, it has in common at least, the graphene honeycomb lattice. What happens, the first experimental observation of the quantum anomalous Hall effect was in magnetically doped topological insulators, which have Dirac cone states in real space on the top and bottom of the surfaces, and the magnetism opens up those Dirac cones and creates a quantum Hall effect. This is the observation of Chui-Zhu Chang and in the group of Chikung Zhu a number of years ago. And so the quantum anomalous Hall effect in magic angle twisted bilayer graphene is qualitatively different in terms of its microscopic origin. Its microscopic origin is Dirac, valley, involves valley polarization. So it involves breaking symmetries in momentum space, this momentum space condensation combined with the Dirac cones at the two different points in momentum space in this system. Yeah, let me comment on this a little further. So in magnetically doped topological insulator, the fundamental source of the broken time reversal symmetry is local moments you intentionally put in the system that order and then create exchange field that couple to the Dirac cones. In magic angle twisted bilayer graphene, although spins do order, which I will comment on if people ask, but the origin of the time reversal symmetry breaking responsible for the quantum anomalous Hall effect is momentum space condensation. It's purely orbital thing. There's no spin or at least the spin magnetism is smaller than the orbital magnetism in these systems, whereas in magnetically doped topological insulator, the spin, like the regular magnets, the spin magnetism is much bigger than the orbital magnetism. That brings up, a possibility of an effect which would really demonstrate that these are orbital magnets and are fundamentally different from any kind of magnet we've ever seen in nature before. And that property is related to the quantum Hall effect and related to something that in the quantum Hall effect literature is known as the Schrader formula. That is that if I have a set of states and a gap, and I have a quantum Hall effect, then the number of states that appear below that gap must depend on magnetic field. And so in the simplest quantum Hall effect, this dependence of density on magnetic field is just the Landau level degeneracy, but this formula is true in Chern insulators as well. And just thermodynamically, that means that the orbital magnetization of a system inside the gap is the same as the derivative of density with respect to field, which is basically proportional to the quantized Hall conductivity. And indeed, this relationship between current and chemical potential basically is what the quantum Hall effect, the way it's observed experimentally. But in this context, what it means is that in these magnetic systems, the magnetization changes rapidly when the chemical potential goes across the energy gap. And there's even reason to expect, and this is an explicit calculation of that since the bulk orbital magnetization is nearly zero because of approximate particle hole symmetry property, this edge magnetization, which is producing a dependence of magnetization on chemical potential in the gap, should be the dominant thing and can allow the sign of the Hall conductivity to change across the gap, which is not something we normally expect in a magnetic insulator, a ferromagnetic insulator, that the magnetization would be changed, sign of magnetization would be changed by small doping. And indeed, this is an observation, a recent preprint from Andre Young's group, Paulschen et al., which shows exactly that going on in these quantum anomalous Hall orbital magnets. Of course, quantum Hall effect was first seen, I realized that there's a slide missing, by the group of David Goldhaber Gordon at Stanford, and now has been seen in several different systems, including by groups by Andre Young and also a group at Berkeley. And so I want to explain what's odd about this graph. The color code here, blue or red, is measuring the sign of the Hall conductivity. And for a system in a weak magnetic field, and the x-axis is gating. So when you go across this line from blue to red, you're going from a slightly n-doped insulator to a slightly p-doped insulator. And what this observation is showing is that what happens is, as you can see in this graph, is that the magnetization of a given state characterized by a given sense of valley polarization, the magnetization changes across the gap. And that means if I use valley polarization as an order parameter, the free energy is switched electrically from having a minimum for one sense of valley polarization to having a minimum for the other sense of valley polarization. And since it turns out the Hall conductivity is related to valley polarization, as perhaps you can understand, that means the Hall conductivity changes. This is very different from normal voltage-controlled magnetic switching, where all you're doing is changing the height of the barrier between two states that are equal in energy. So this is an unusual property. Mr. Chairman, how much time do I have?
Including questions, we have to be done in 10 minutes. But
okay.
I think, yeah.
So let me skip this or go quickly through this. I just mentioned that this is what I think is an open question. I said that the insulating states break flavor symmetries. there's indications from, for example, Shubnikov to Haas pointed to very early that even in the metallic states, the fourfold spin valley flavor symmetries are broken in this system. This is actually a mean field calculation for metallic states of the energy as a function of filling factor. And the blue curve allows all symmetries, to break, and gives a picture where the chemical potential has a jump. In other words, there's a gap. This is just taking the first derivative of the curve I just showed you at all integer filling factors. This is going from -4 to 0. Here, this is a experimental plot going from -4 to 4 of a scanning probe or chemical potential measurement here in blue from the Alani group. And it shows these chemical potential jumps, which you are naturally expect associated with gaps, more or less agrees with what you should expect from mean field theory, and but doesn't see chemical potential jumps at the quarters, at these points. I think we may hear in something about this in the next talk by Ali Yazani about the question of whether or not gap states at the quarters are fairly universal in these systems. And the derivative of chemical potential with respect to density has these peaks, which can be easily used to identify gap states and appear in these mean field calculations. And as I mentioned, so all of that notion that flavor symmetries are common in the metallic regime is also supported, as I mentioned, by Shubnikov to Haas. And here's an example of one of the Hall density measurements in the literature. And these jumps in the Hall density, which suggest a resetting of the Fermi surface, are also very strongly suggestive of, that all of these jumps, big jumps, can be due to Van Hove singularities, but they may also be due to broken flavor symmetry. So Hall density measurements actually give you some clue about where, as a function of filling factor, the metallic states have broken flavor symmetries. But photo emission would be even better. I'm going to have to skip these things about the interpretation of the Hall effect. And let me just mention in my last minutes something about the linear in T resistivity, which is one of the very intriguing properties in magic angle twisted bilayer graphene. This is a summary of observations that have been made by a number of people. And what this inset here shows is that the linear in T resistivity occurs over a broad range of band fillings. It occurs only close to the magic angle. It's a very dramatic effect compared to the temperature-dependent resistivities you see at other twist angles. It shows that there's lots of inelastic low energy scattering. That's maybe the most neutral interpretation you could make. And one of the ideas that has been proposed to explain this is that it could be caused by electron-phonon scattering if you have very small Fermi surfaces, and to scatter electron from K to K plus Q emits or is associated with the presence of phonons with wave vector Q. And you can explain linear in T resistivity of all of the phonons that, if all of the phonons that can connect states at the Fermi level have an energy much less than KT. That would give you linear in T resistivity, just like you see in normal metals above the Debye temperature. But I want to show you something on the next slide, which is an examination of the degree to which this remains true when you take account of the fact that the states in these moires are not momentum eigenstates. Instead, they're linear, they're periodic functions in the Moiré cell. You can write them as a linear combination of many different momenta separated by reciprocal lattice vectors. And you actually can excite transitions across the Fermi level with many different phonons with energies much bigger than, wave vectors much bigger than the size of the Fermi surface. And this is an explicit calculation of that effect by Wei Jin and my group. Sorry, I left the reference off. This should be on the archive shortly. And what it shows is that if you didn't include umklapp, then you would get fairly convincing linear and T resistivity over a wide range of band filling factor, parameterized chemical potential here. But when you include the this umklapp effect, you only get linear and T resistivity, very close when you have a chemical potential very close to 0. These are actually calculated with the single particle band, so that would give a very small Fermi surface near the kappa points in the Brouin zone. I'm going to end with this observation. Here's a wild idea, if you like. This is a calculation by Ajesh Kumar Mingshi and Mingshi in my group. It's been hanging around for a while. We hope to get it on the archive soon. But what it is a calculation of, with only one state, one band per, one electron per Moiré in the flat bands. In other words, 1 out of 8 bands occupied and breaking valley and spin degeneracy, and looking at the collective mode spectrum. And the very surprising thing about these results, at least for me, is this. I'm going to just talk about this green curve. This green curve is an interband collective excitation. Can be viewed as some kind of bosonic object that would act with quasi-particles. These bosonic excitations, this is sort of valence to conduction. You can view it as an exciton if you like. And there's one of these modes for every momentum in the Brouin zone. This is actually calculated in an insulating state. You can also calculate these modes in metallic states where they have somewhat lower energy. And these modes have the potential to explain the linear and T resistivity, because they only exist in the Moiré Brouin zone. And they have a nice low energy that can produce lots of inelastic scattering. And the wild idea is that maybe this has something to do with superconductivity in these systems. So we're playing in my group with that wild idea. And with that, I can see Dima's getting nervous, and I'm going to stop.
Okay, thanks very much, Allan. I think we have really just 3 minutes for questions now. So I'll maybe connect Nelia Fernandez. You have a question?
Okay. Hi.
Yep.
Can you hear me?
Hi.
Yes, thank you. I particularly want to ask regarding the twisted bilayer graphene and the superconductivity and the relation with the flat bands, because especially earlier you mentioned something about that the flat bands they don't touch at some points in the energy spectrum, and then for example, if you apply strain, they can even separate. So I wonder, yes, I don't know if this is the right way of making the question, but how flat should the bands be, and what's the limit? I mean, in which you can just lose this property that will give you correlations.
Yeah, I think that we know the answer kind of experimentally. Maybe Dima can correct me, but I think we know that superconductivity occurs at least over a 10% variation in twist angle, maybe somewhat more near the magic angle. And I think we also know that the orbital character of of the flat bands is consistent across the Brouin zone over that angle range. So the bands are flat, but the orbital character of these bands that is important in producing these, surprising localized excitonic degrees of freedom that live on the triangular lattice is, I think, is a property of these wave functions. I think you'll hear later in the meeting about some other ideas which also, try to connect superconductivity to the orbital character of the wave functions in the flat band, much like fractional quantum Hall effect is related to the orbital character of states in the Landau level.
Okay, so it's actually related to an excitonic nature.
I think it's certainly, my guess is superconductivity is very intimately related to the nature of the wave functions and how they that exist in these two flat bands. Yeah.
Okay.
And that persists also over at least 10, maybe more percentage of twist angle.
Okay.
Okay, maybe next question by Oscar Wafek. Oscar? Hello, Oscar? No?
Okay, Oscar.
Oscar,
send me an
yeah.
email.
Okay, I think, yeah. And then maybe the last question by Christian Nowakovsky. Christian? Okay, probably also by accident. Okay, with this we're... Huh?
Can you hear me now?
Yeah, please go ahead.
I had a question about that part when you were talking about the gap at the charge neutrality point, and basically it is related to slowing down of the electrons. Is that correct?
Yes, that's what I said anyway.
So should the size of the gap at charge neutrality point could be used as a measure of the flatness of the band of the samples?
I think that the size of the gap is mostly related to the strength of electron-electron interactions. And then, as our chair has demonstrated, that can be changed quite a bit. And the superconductivity is sensitive also to that, as you'll no doubt hear more about as we go along. Yeah, so I don't think, the size of the gap tells you much about the flatness of the band. In fact, we think the gaps are usually bigger than the bandwidths.
Yes, I see. Okay, so the gap at the charge neutrality is mostly due to interactions, and this is indirectly connected to the flatness of the band. Okay, thank you.
Okay, thank you very much. So,
can I ask my question?
Oh, Oscar. Okay, there you are. Okay.
Hi, everyone. Sorry, my computer froze for a second.
Okay.
So, Alan, a beautiful talk. Question about the magnetization switching by density. If we were to turn off the external magnetic field in this theoretical picture, would the magnetization switch?
No,
I guess
it's due to coupling of the magnetization with the external magnetic field.
Right. I thought that there was an experiment by Corrugatian's group where they see the magnetization switching without the external field. Is that correct?
Yeah, the magnetization, or maybe you're thinking of, they saw the anomalous Hall effect change sign. Right. Is that right?
That's right.
That's what, of course, that's what people measure.
That's right.
Yeah,
that's right.
But so that easily can happen by accident. The anomalous Hall effect is, some function of density, but that behavior is not hysteretic. So here, in these experiments, there's a demonstration that the sense of valley polarization has been switched. And the evidence for that is the hysteretic property of this dependence on voltage.
I see. Thank you.
Yeah.
Okay. Thank you very much for the questions,
Okay,
and thank
yeah.
you very much, Allan, for the excellent talk. And we'll move on in 10 minutes to Ali Yazdani. So everybody must have follow the other link, which is linked with Ali Yazdani. And we're going to start sharp at 4:30. So this is basically in about 10 minutes. And we'll zoom out now and we'll start preparing Ali for his talk. See you soon.
Thanks,
right.
everyone. Please send emails if you have thoughts.